Quantum thermodynamics, energy physics in the quantum realm. Title: Quantum thermodynamics, energy physics in the quantum realm. Introduction, 100 words. Quantum mechanics, a fundamental theory in physics, has revolutionized our understanding of the microscopic world. It successfully explains the behaviors, interactions, and properties of particles at the atomic and subatomic levels. However, as physicists delved deeper into the quantum realm, they realized that the laws of classical thermodynamics needed to be reconsidered. This realization led to the birth of a new field of study known as quantum thermodynamics. In this article, we will explore the fascinating world of quantum thermodynamics and how it offers unique insights into energy pH. Physics at the quantum level. Quantum thermodynamics explained, 300 words. Quantum thermodynamics is a branch of physics that investigates energy transfer, work, and heat at the quantum level. While classical thermodynamics deals with systems consisting of a large number of particles, quantum thermodynamics tackles systems composed of individual quantum particles. It combines the principles of quantum mechanics and thermodynamics to understand the thermodynamic properties of such systems. One of the key differences between classical and quantum thermodynamics lies in the concept of energy exchange. In classical systems, energy transfer occurs in a continuous and deterministic manner. Following the laws of thermodynamics. However, in the quantum realm, energy exchange is described by the probabilistic nature of quantum mechanics, introducing uncertainty and fluctuations. Uncertainty and fluctuations in quantum thermodynamics, 300 words. Quantum thermodynamics introduces the concept of uncertainty in energy measurements. According to Heisenberg's uncertainty principle, it is impossible to precisely know both the energy and time of a quantum particle simultaneously. This principle poses challenges when defining quantities like heat and work, as they involve energy measurements. As a result, the usual definitions of classical thermodynamics no longer hold true at the quantum level. In addition to uncertainty, quantum thermodynamics also deals with fluctuations. Fluctuations in energy, temperature, and other thermodynamic quantities become significant as systems reach the 2n2 m scale. Understanding and characterizing these fluctuations are crucial for accurately describing energy transfer processes and extracting useful work from quantum systems. Applications of quantum thermodynamics, 400 words. Quantum thermodynamics has far-reaching implications and potential applications in various fields of research. One area that has gained significant attention is quantum computation. The fundamental limits of energy consumption and dissipation in quantum computers can be understood using quantum thermodynamics principles. By incorporating these limits into the design of quantum algorithms and devices, more efficient and powerful quantum computers can be developed. Furthermore, quantum thermodynamics plays a critical role in quantum information theory. Quantum communication protocols, such as quantum teleportation and quantum cryptography, rely on encoding information into quantum systems. Understanding the thermodynamic constraints of these processes ensures that energy is utilized optimally to maintain the security and fidelity of quantum information transmission. Another promising application lies in exploring energy harvesting from quantum systems. Quantum thermodynamics sheds light on quantum heat engines, systems that convert temperature differences into usable work. By leveraging quantum effects, such as quantum coherence and entanglement, researchers aim to create more efficient and powerful energy conversion devices. Challenges and future directions, 300 words. While quantum thermodynamics offers exciting opportunities, it also comes with unique challenges. One such challenge is the complexity of quantum systems, which often require advanced mathematical techniques to analyze. Moreover, experimental verification of quantum thermodynamics is another significant challenge. Quantum systems are delicate, easily disrupted by external influences, and hard to manipulate effectively. Creating and controlling such systems to perform specific thermodynamic operations remains an active area of research. Despite these challenges, the field of quantum thermodynamics holds immense promise for the future. Quantum thermodynamics and the quantum vacuum state, 400 words. In addition to its applications in various fields, quantum thermodynamics also has implications for the study of the quantum vacuum state. The vacuum state, often referred to as the lowest energy state, exhibits intriguing characteristics in the quantum realm. Quantum fluctuations in the vacuum state give rise to the creation and annihilation of virtual particles. The study of quantum thermodynamics allows us to understand the thermodynamic properties of the vacuum state. For example, the vacuum fluctuations have been linked to the phenomenon of Hawking radiation, where black holes emit radiation due to quantum effects near their event horizons. By applying concepts from quantum thermodynamics, researchers have been able to model and predict the behavior of Hawking radiation. Furthermore, the vacuum state has an inherent energy, known as vacuum energy, which arises from the quantum fluctuations. Understanding the thermodynamics of the vacuum state is not only of theoretical interest but also has practical implications. The vacuum fluctuations can be harnessed for practical applications, such as in the development of nanoscale devices and sensors. By carefully designing setups that take advantage of the fluctuations, researchers can explore novel energy transfer processes and enhance the performance of these devices. Future directions in the field of quantum thermodynamics involving the vacuum state include studying the interplay between quantum information and energy fluctuations. Quantum information theory has highlighted the deep connection between information and energy, and applying these principles to the vacuum state may lead to new insights and applications. Furthermore, exploring the thermodynamics of highly non-equilibrium quantum systems, such as those excited by ultrafast lasers or trapped ions, is an exciting frontier. These systems pose interesting challenges in terms of energy transfer processes, as they can exhibit behaviors that deviate significantly from equilibrium. Looking ahead, quantum thermodynamics and quantum phase transitions, 300 words. In addition to the previous discussions on quantum thermodynamics, another fascinating aspect of the field lies in its connection to quantum phase transitions. Quantum phase transitions occur at ultra-low temperatures when quantum fluctuations dominate the behavior of a system, causing a sudden change in its physical properties. Quantum thermodynamics provides a powerful framework for studying and understanding quantum phase transitions. It allows us to investigate how the energy physics of a system evolves as it goes through different phases. By analyzing the thermodynamic properties of quantum phase transitions, researchers can gain insights into the underlying quantum phenomena and the nature of quantum criticality. The study of quantum phase transitions and their connection to quantum thermodynamics has broad implications. It has relevance not only for fundamental physics but also for materials science and quant and matter physics. Understanding how the energy physics of materials changes during phase transitions can help researchers design and develop new materials with specific properties. Additionally, the combination of quantum thermodynamics and quantum phase transitions has opened up new avenues for the study of topological phases of matter. Topological phases are exotic states of matter that exhibit unique properties, such as robust edge states and protected information transfer. By incorporating quantum thermodynamics into the study of topological phases, researchers can probe the thermodynamic signatures of these states and explore their energy transfer processes. This knowledge is essential for the development of topological quantum devices, which have potential applications in quantum computing, information processing, and quantum communication. These systems exhibit intricate energy physics, and unraveling their thermodynamic properties will require advanced theoretical and experimental techniques.